Yes. So let's continue further. So yes. So the last time we did till we understood what are measures and how are measures being formed. Okay. So let's see one example, one theorem. So this is a very important theorem. What does this theorem says? Let's see the collection of closed rectangles of Rn, where R belongs to C in volume of R denote the volume of VR denote the volume of R. Mu star is defined by this. Let C be a collection of closed rectangle. Means there are lots and lots and lots of rectangles. Then say a rectangle, and inside this it consists of many rectangles. Okay? And they are closed sets. Closed means you can say it also consists the boundary points of each set. And suppose there is one rectangle inside this, and let's denote it with R. Let's denote it with R. R belongs to C. These are the collection of sets. So you can say rectangles. This black ones are rectangles, and inside this one rectangle is it's R. And this VR, okay, VR, you can say denotes the volume of R, okay, the volume of R. And the measure is defined by summation of volume of CK. It means this C rectangle. Okay? There are many rectangles. Okay? And let's sum the volume of each rectangle. Suppose in this case there are three rectangles. So let's sum this. Like take the first rectangle, take the volume, take the second rectangle, take the volume, third rectangle, take the volume. Okay? And then you sum it off, add it. Okay, CK belongs to C. Means every rectangles belongs to C. This C means this larger rectangle. Every rectangles are contained in the single, you can say. And the union of K, it means union of all the volume, union of all the rectangle consists of subset of A is consisting of in the union of K. You can say, so let's take a small element. You can say, let's take A like this. Okay. This is one more rectangle. So you can say if A is a subset of union of all the rectangles. So you can say like a small book is kept, like you can think of it like A is a small book. Okay. On the table, there is a big table, and on the big table, we are keeping a large book. Okay. And up of that one smaller book, up of that one smaller book, and up of that one smaller book, and one smaller book. So this the smaller book will will be contained in all the other books, right? So this is what is it is telling. And the infimum, you can say infimum is the greatest lower bound, and you take the summation of the smallest number. You can say when you add them, like when you start adding the volume of each of this rectangle and take the smallest value, okay, that will be the measure of A, of course, right? So when you will start, let's add A. Suppose this is a C, the larger rectangle, and this A is the smallest rectangle. So let's start taking the volume of this. It will have some volume, right? The pink one, larger one, it will have some volume. Then a third rectangle, this one will be have some volume. Then fourth will have some volume, and fifth will have some volume. And you add it all. Okay. What will be the measure of A? What will be the measure of A? You can say it will be the smallest value. This will have some value. This will have some bigger value, pink one. This black rectangle will have some big value. The smallest rectangle will have the smallest value. And that is known as greatest lower bound. You can think of it like this. Okay. So we can see this from this visuals, right? A is a subset of Rn. We can see it from here. And CK, V is A is a subset of Rn, and A is not a null set. It consists of some values. Then mu star is exterior measure of on Rn. Okay? If this happens, like there are rectangles and measure of A is the infimum, then the exterior measure on Rn, it means you can say a cover that is, you can say this larger rectangle that is covering. Okay, the measure of the larger rectangle would be denoted by mu star. The measure of means the cover required to cover this exterior measure of Rn. The condition is A should be a subset of Rn. So let's try understanding the proof first. So mu star is defined by mu star A and infimum of this of course, right? Infimum of volume of CK. Means take the whole rectangle, every rectangles, and infimum is the smallest one that is covering the A. And it is a closed rectangle. You can see it, right? Where A is a subset of Rn, and it is an exterior measure of on Rn. Right? A is a subset of Rn, and it is an exterior measure of Rn. It is on an exterior measure of Rn. We first show that, so you have to prove that we have this, there is something mu star that is covering the whole rectangle. So let's show it. So we take the volume, the summation of volume, okay, and CK is closed set. A is a subset of CK. A is a subset of CK, and it is not equal to null set. Take the volume of CK means take the volume of all the rectangles. This rectangle, this rectangle, this. And A is also a subset of, as you can see, A is also subset of all the rectangles. A is consisting in all the rectangles. Okay? A is a subset of Rn. Let RK rectangle with side length K and contour origin, center origin. Okay, it means you can say there is one rectangle. Let RK means every rectangle in this pink rectangle that is starting from this. It consists of a side length L. Okay, side length L. Sorry, side length K. Okay? And union of such RK means union of all the rectangles, with K, with side K means this rectangle, this black rectangle, second rectangle, third rectangle, fourth rectangle. This, and if you take the union, you will find that it will keep on going and it covers the whole C. As you can see, let C be a closed collection of rectangle of Rn, real numbers. Okay? So it is saying that all the rectangles have side length k of Rn. Means this rectangle, this, it all has Rk, uh, length k. Then for any A subset of Rn, any A, let's take this A. Okay? It is a subset of Rn. Yeah, it's a real number. It's saying it consists of union of Rk. What it is saying that A is a subset of Rn, means is a real number. Okay? And we have rectangles like this first large rectangle, then smaller, and the pink one, and the smallest one A. So you can say it like if all the rectangles have k, length k, then this A consists on all the rectangles. This rectangle is placed on all the rectangles, as you can see from the diagram. This A is placed here, and it's placed in also in this pink rectangle. It's also placed in the second rectangle, third rectangle, fourth rectangle. You can think of it like piles of books placed on each other. Okay. So you can say that RK covers A. So you can RK covers K. RK covers K. So if this rectangle is placed on pink and this pink rectangle is placed on black and this is placed on the third and this is placed on the fourth, so you can say that A, this place occupied by A is present on every rectangle, right? A is placed on top of the other, right? So we can say that it is union. A is present in every other K, RK. So this is how we denote it. Right? So this is what it is saying. So you can say RK covers A. Yes, we can see this whole RK is covering A, right? So if it is placed on every other rectangle, it is also been covered by every other, you can say, rectangle. So you can think it like, suppose this is a rectangle, okay? And if on this you are placing another rectangle, and on this you are placing another rectangle. So this has a presence on this rectangle as well. You can say this, the part of this rectangle, the second rectangle. If you draw the second rectangle like this, so this part will be denoted for the first rectangle. So this small rectangle is placed on first rectangle and second rectangle as well. So you can say that every rectangle covers this small rectangle. And we can say that volume of CK is closed rectangle. A is a subset of this is not equal to null set. So as RK is covering A, it is covering A, right? It is covering A. If it would be a null set, then as we saw that it is zero, the measure would be zero. But it is covering, right? It is not a null set. If it is covering, then it has some value, and it is not a null set. This is what is saying like this. Okay, understood that A has, now we understood like A has some measures. Okay, that's good. Now what? Now how you would prove that the volume of this measure is, if this is the A is an element of this rectangles, then how would you prove that the C is consists of a measure, U star? So by the measuring properties. Okay. First, we proved that A, in step one, we proved that A is not a null set. Okay, A is not a null set and it is covering. It has a cover. Next, we would prove that there is a null set. So from here you can see that there are three properties. If these three properties are satisfied, then it is a measuring. You can say this. It has a measure. Okay. So now first we prove that it is not a null set as it was given in the theorem itself. So now let's go for here. Okay, and let's prove how it is not equal to zero. Sorry, the null set is equal to zero. The measure of nothing is always zero. Okay? So if it is covering this and it has a null set, okay, R covers null set as well. So let's prove this. Let epsilon naught would be greater than zero. Okay, and let there are some rectangles, so smaller rectangles in this, in this, the whole, in all the rectangles, there are some rectangles you can say has a boundary length of epsilon naught. Okay, like this, like this. It has a boundary length. Epsilon naught is the boundary length. It's saying like this. Be a rectangle Rn with volume R. It has some volume and its volume consists of a real number. And that real number is, as it is zero, it means it's consists nothing in it. Zero means it's empty. There is no value inside this. And just it has a boundary. That is, the value is only on the boundary that is epsilon naught. So we are saying the volume would be epsilon naught, right? So if it is zero, nothing is there in this, and only a boundary, that is epsilon naught. So what would be the space occupied with this? It will be always the length of this boundary, that is epsilon naught, right? And this covering this, and you can say that if it is zero, right, it is nothing, and the of this nothing, measure of this nothing would be less than this boundary, right? It means it is covering the inside part of this boundary. It is covering the inside part. It will always be less than epsilon naught. If it is zero, it means it's nothing. And it has a boundary epsilon naught. So if there is a cover, the cover will cover the rectangle inside, which is less than epsilon naught. For all epsilon naught is a value, it is not zero, it is greater than zero. If this is the case, then you can say that measure of a null set in why? Because there is nothing and there is no value nothing. The measure would be zero. Correct? We proved this property that it has measure zero. To prove actually a measure, whereas these properties needs to be satisfied. Now we would prove monotonicity. Okay? Monotonicity means if A is a subset of B, then this measure of A is also measure of B. This is how we will prove this. Let's go. So to prove that, let's bring one set A, one set B. A is a subset of B, B is a subset of real numbers, Rn. And you have to show this monotonicity property. So this is very interesting. Let's take a rectangle. Okay. And let's take a rectangle in this. Okay. So these rectangles are all it is happening here in this bigger one. So there's no space to draw and trying to explain here. So let's take a rectangle B. And let's take a rectangle A. Okay? And we have to show that measure of A, okay, measure of A is a subset of measure of B. Okay, you can see it, right? It's, of course, you can see it in the diagram. Measure of this measure of A is a subset of measure of B. You can think of it like there is a book placed on a table, small book, and above that, okay, on suppose there is a large book, okay, and above that there is a small book, and you are covering it with a gift wrapper. So when you cover it with a gift wrapper, it will cover both a small book and it will cover the larger book as well. So the cover required to cover the small book will take the same space in B as well. Okay? There would be no changes in space. Okay? So you can say that it is covering B as well. So if CK covers B, if there is a cover, okay, if CK covers B, if it is covering B, then of course it will cover the A as well. B is a larger part and A is a smaller part, right? And if we take the volume inside B, say B is a union of CK. CK is a rectangles, so CK is a set of rectangles, and A and B are there in these rectangles. So that's why it's saying that if B is placed here, it is a union of all the rectangles. So if B is a subset of CK, then it is also uh, there in A as well, because A is smaller, A's volume is smaller, and B's volume is bigger. So A's volume will be there in B's volume as well. And the next part says that infimum of B. If you take the smallest value of B, the smallest value of B, suppose smallest value would be volume. You can think of it like B has a volume, and the volume would be always be greater than the volume of A. The volume of B would be always be greater than volume of A. Okay, infimum means the smallest volume of B. Even if the smallest volume of B would be greater than the volume of A. Correct? And if this is the case, then we can say that measure of A is less than measure of B. So if volume of B is greater than volume of A, volume of this book, B book, is greater than volume of A book. Because you're keeping a book A, and above that you're keeping a book, another book B. So volume of this, the smaller book, is the volume of larger book is greater than A. So you can say that it is consisting in the smaller rectangle A is consisting in B. Okay? Think of it like a book, a large book that is kept on a table, and a small book that is kept on it, right? And we can say that there is a large book like this, and there is a small book like this. So if the volume, the space occupied by the large book, if it is greater, large book is greater than small book, as you can see. So we can say that the volume of this large book is greater than small book, then this measure required, or you can say this small book is kept on this large book. The small book is kept on this large book. And the measure means if you're covering it with a gift wrapper, if you're covering this with this gift wrapper, it will always be smaller than the gift wrapper required to cover the larger rectangle. That's it. Correct? And yes, so we proved the second part as well. That is monotonicity. Okay. What does monotonicity says? Measure of A should be measure of B, the subset of measure of B. Now let's do the most interesting part. That is the, let's say, union of an is less than equal to summation of an. I explained you earlier as well. We have to prove this in here. So it's very simple. So yes, to prove that, what we have to prove, union of an is equals to summation of each of that an. Okay. So let's first define let A and be a sequence of subsets of Rn. Okay. Suppose real number, talking about real number, right? Subsequence of Rn. Okay. So okay, we are talking about rectangles. So let's say that this is a small, uh, okay, small set. This is all happening inside the bigger rectangle. Okay. This suppose imagine on this any part of this it is happening. So let's take a bigger rectangle. Let's note this A1. Take the larger rectangle, name it as A2. Now take some other rectangle, A3. Okay. Like this way, you can keep on increasing the rectangles till AN, till infinity. We have to show that union of all these rectangles. If you take the length of this, measure of this, A1, take the measure of this, A2, and you take the measure of the largest rectangle. That will be, and if you cover it up, okay, you take the length of this, and we take the length of this, cover of this, and you take the cover of this. And you keep on doing this till the nth part. Okay. So you can say that this covers A1, second cover A2, and the third cover AC. And if you add cover of A1, add cover of A2, and add cover of A3, you can say you can get the whole cover of the A3. Right? If there are many rectangles, you can get the cover of the largest rectangle. So if union of this is less than equal to summation of each of the rectangles, like I have explained earlier also with an example, like uh, this is A union B, right? A union B, and you have to keep on adding it. A1 plus AB, A plus B. So this is what, and this is summation of this is epsilon naught. So let's take a greater than 0 by this. Now cover of this of An such that there exists a cover of Rn. Remember there is an epsilon naught greater than 0 definition of U star such that the volume of Rn, okay, is less than measure of volume of Rn is measured than volume of N. There exists a cover Rn of An. Suppose there is a, you can say Rn as we are talking about this one. This Rn means suppose there is some rectangle of real numbers and suppose this An is there, right? A1, A2, A3, A4, and we take a cover Rn. So let's define this cover by this, like we have done this Rn. Suppose there is one cover that is placed on this rectangle, okay, and it will be the summation of volume of cover. this cover is placed on each of these rectangles, the volume would be less than measure of AN, measure of the largest rectangle, plus one small error amount, plus a small number you can say. So measure would be not be greater than this larger rectangle. It means that the volume of all the cover that is placed on this will not be greater than this. Okay? Then, if that's the case, then you take the union of each cover. What does this mean? Union of each cover. If you take each cover on each rectangle and you take the union of that, it will cover all the AN. Okay, and that measure of AN, the largest rectangle, would be less than equal to summation of each of the cover. Summation of summation and in bracket summation of volume of Rn means a cover that is covering each and every element. A1, A2, A3. It will be always be less than that, equal to that, less than or equal to. It's simply meaning that measure of AN, measure of the largest rectangle, is less than equal to individual sum of cover of every set. And if that's the case, then this cover would be less than equal to this, as we have already mentioned that here. And if this is the case, then you can also write it like this, summation of every cover. It means the for every element, the error term you can say keeps on adding. And you can simply write it like this, and you can simply write it. If you ignore this absolute not, it is always less than equal to the summation of this. And hence the measure of union of every AN is less than equal to summation of measure of AN. Hence this is true. I hope you enjoyed this lecture.